Good afternoon, everyone. Thank you for joining. So today, I'm going to talk about some methods for measuring how much a generic system reveals about its secret inputs. And we'll work under a black box assumption. So we'll assume essentially no knowledge of the internals of the system. And the main result, really, of our work is that we can actually use machine learning for measuring this leakage in an efficient way, but still retaining strong theoretical guarantees. So, as I said, we consider a black box system. Now, as a system, you could think of a computer program. This could be a function. It could even be some hardware doing some sort of computation. And this system takes as input some secret, and it returns some output. And the output, given the secret input, will be chosen according to some probability distribution, which is unknown to us. And for the purpose of this talk, the secret will take finite values from a finite set, and the outputs can be either discrete or continuous values. And we really make many assumptions on these systems. We actually ask that this system doesn't change over time. That's all, really. And now the kind of questions we try to answer here are, well, say an adversary observes the output. Well, can we measure how much the output reveals about the corresponding secret? Or to phrase it kind of similarly, how hard is it for an adversary to predict the secret given the output? Now, this is, of course, a very general model, and it has several applications. Just to name a few, we have location privacy, so where the system could be a location privacy defense mechanism, which takes as input the location of a user, adds some noise, and returns a noisy location. And the beauty of this sort of model is that we don't really care about what's happening inside this system or how this noise is generated. And the goal, in this case, of course, of the adversary is to predict the true location of the user given the noisy version. Another example, of course, is side channels, and we are in the right session. So the one you see here is a simple timing side channel where the adversary tries to infer, say, the secret key given the computation time of some encryption cryptographic primitive. And finally, a particular case of side channel is network analysis, in which case the adversary may try to infer perhaps user behavior, which web page a user visits, given the encrypted network traffic. So we said that we would like to say something about the probability that an adversary can guess the secret given the corresponding output. And in this talk, I will just talk about the complement of this. So we'll look at the probability that he guesses incorrectly. But of course, we're not interested in just one adversary. We're interested potentially in all the adversaries. And in general, we call base risk the probability of error of the optimal adversary under this scenario. And on the basis of the base risk, we can actually derive some leakage measures, such as mean entropy leakage. So really, our goal now will be to estimate the base risk for a system. But now, of course, we only have a black box system. So what we will do is, well, we will make some queries to the system with our choices of secrets and look at the respective outputs. And from this sort of input-outputs data set, we will want to estimate the base risk. Now, there are two things we would like from an estimator. First of all, we would like that for any system, its value should converge to the base risk, given enough examples. But of course, B, for real-world systems, we would like this estimator to converge quite quickly. So we wouldn't want to make too many queries to our system. And Until now, really, there's only been one method for doing this sort of estimation, and that's what we refer to as the frequencies paradigm. So let me give you an idea of how it works. So suppose we're given these queries, input-output queries, and then we ask this frequencies adversary to make a prediction for an output 0.4. Then this adversary will simply do a majority vote over the secrets observed with that output, and it will just output that secret. But of course, problems start arising when we ask this adversary to make a prediction for some value, for some output value it has never seen, such as 0.5, in which case you'll have to randomly guess. Now, this really has been the only approach so far in this direction. But unfortunately, well, A, of course, it cannot be applied to whenever the output space is continuous. This is easy to see. But secondly, and perhaps most importantly from a practical perspective, these kind of methods really needs to have observed one example for each possible output value. And of course, if the output space of the system becomes very large, then this method will just not scale. It will just require too many queries. So what can we do about this? Well, let me tell you a bit about this nice little classifier, nearest neighbor. This is arguably the simplest machine learning classifier. And the idea is as follows. So say we have some points, each belonging to a different class. And we have to make a prediction for a new point. Then the nearest neighbor rule will tell us, well, just output the class of the closest observation to your point. Now, why am I talking about nearest neighbor? Well, as a matter of fact, we showed that in our paper, we showed that with very, very minor modifications, the error of the nearest neighbor classifier asymptotically approximates the base risk. So effectively, we can use the nearest neighbor classifier as we were using the frequencies approach for estimating the base risk. So this is the idea. We have made our queries to the model. We have this data set. We will have to split it into training and test set, and then estimate the nearest neighbor error on this test set. And this will already be a leakage measure for us. Now, this only works when the output take values from a finite space, similarly to the frequencies approach. But then, if we have continuous output values, we can just use K and N. So K and N works similarly as before. Just this time, we will make a majority vote over the K closest observations. And in our paper, we showed that if we choose the value of K appropriately with respect to the size of the training set of K and N, you could think of in terms of the number of queries we make, then K and N is a leakage estimator, even in the continuous case. And this really brings us to our main result, and that is that, as it turns out, there exists a whole class of machine learning methods which have this property, and that is that given enough examples, given enough queries, their probability of error approximates asymptotically the base risk. So these are the theoretical guarantees that we wanted. Now let's look at some actual results in practice. And within the paper, we looked at a couple of side channels. I'm just going to talk here about a location privacy example. So in this application, we looked at the Gowalla dataset, which comprises users' location data. And to this location data, we applied several location privacy mechanisms, geometric, Laplacian, and BLEAU Arimoto. So let's start with the first one, geometric. The idea is, suppose you have two users' locations to defend, then the noise is sampled according to the two distributions you see here. And, well, we run the experiments and computed the number of queries required for our methods to actually converge to a good approximation of the base risk. And, well, as it turns out, neither frequentist nor nearest neighbor approach did actually manage to converge within the number of examples we had. But with k-nearest neighbor, we were able to converge within 20,000 queries to the black box. We also run some experiments for the Laplacian noise, which is essentially equivalent to the geometric noise. It's just continuous. In this case, we had pretty much the same results, although we couldn't really apply the frequentist approach because, of course, this is a continuous mechanism. And note that in these examples I'm showing you here, nearest neighbor is always performing very badly, but in the paper you'll find examples where nearest neighbor was better than KNN. And finally, we applied our techniques to this mechanism, which is just some iterative mechanism which maps a user location into one of the points you see there together with their distribution. And in this case, well, we saw something weird. Well, pretty much all the methods were equivalent, although still KNN was slightly better. So why is this the case? Well, if you think about it, in this case, the system has only very few possible output values. And indeed, the ones you see plotted here are the only possible values this system can have. And this is actually a fact we observed much more in general, and that is that our methods, and in general machine learning methods, tend to be equivalent to the frequentist approach for very small systems, or for systems for which the output space is fairly small. Right, so we also carried on some experiments on synthetic data. I'm just going to give you the gist of it. We observed that, and this is not so much of a surprise, that machine learning methods, and in particular nearest neighbor methods that we evaluated, did manage to scale to very large systems, so system with 100,000 output values, 1 million output values. And they were particularly good whenever there was some sort of metric on the output which could be exploited. So you could imagine time side channels when the output is time. When there was no metric on the output space, then our methods were pretty much equivalent to the frequentist approach, which was not bad news. But still, we were able to find some particular example. We crafted this very weird system so that nearest neighbor rule could fail against the frequentist approach. At which point, one may ask, well, is there an optimal estimator for black box security? And the answer, once again, comes from the machine learning theory, where the no-free-lunch theorem tell us, no, there's no such thing as an optimal estimator. And indeed, what it says is, imagine you have any two estimators, A and B. There's exactly as many systems for which estimator A will be better than B, and the other way around. And the takeaway, really, of this impossibility result is that in practice, when we want to measure the leakage with black box security methods, we should always try just many estimators and just look at the one that converges faster. But this is, of course, kind of good news if you think about the fact that after our work, there are many, many new estimators for estimating the leakage. And indeed, there is a whole new class of estimators. And we released BLEAU, which is a tool for measuring leakage. At the moment, it only implements nearest neighbor methods, but it's based exactly on this idea. So kind of to wrap things up, black box security has a huge potential because it allows us to measure the leakage of systems without the need to model them, their internals. And of course, this is good in practice where sometimes systems are just too complex to analyze formally. And until now, there was only the frequencies approach for measuring leakage in this way. But thanks to this work, there's a whole new class of methods, and namely the universally consistent machine learning rules, which we can use for this purpose. And in the future, really, we are looking forward to more applications in side channels, but we're also looking at using these techniques for measuring the security of machine learning against attacks such as membership inference, for example. So this is really all from me. I'll be happy to take your questions.
Thank you. We have plenty of time for questions. Oh, sure.
Hi, Tom Benjamin, Perspective Labs. Loved the presentation. Question about what happens to your model in certain kinds of cases. So I'm curious, just in the example of the location privacy, what happens to what it is that your model is trying to express when you add in additional auxiliary information, like the fact that the person is more likely to be in the Walmart than the lake across the street?
Okay. So the idea is that by measuring the leakage, right, we try to measure how much more information an adversary has once he observes the output, right? Now, of course, he may have auxiliary information of which we do not know. For all we know, he could know immediately the secret, right? So in that case, this, the knowledge of the output wouldn't give him any additional kind of information. So I'm not sure if this answered the questions. Yeah, okay, that's good, okay.
Somewhat similar question. So you're assuming black box adversaries, but if they have more information, not necessarily about auxiliary information about the input, but about the black box, what does that do to the guarantees?
Right. So as a matter of fact, the base, when we talk about base risk or leakage, whatever we're trying to estimate, that also holds for white box adversaries. So the optimal adversary is called the base adversary, is one who knows exactly all the internal probability distributions or knows the internal algorithm, right? So what we are estimating here does hold for white box, yes.
Great. Okay, unless there's any other questions, then why don't we thank Giovanni again.